Hi everyone, welcome back to Stats. So for this week, we're going to be talking about linear regression. And Raja might pop in a little bit in this video, but he's being very sleepy. So for the most part, I'm just going to leave him sitting on my lap, and maybe he can pop in at the end to say goodbye to everyone at the end of this video. So that's okay. You can take a little bit of a nap. That's all right. So we're going to be talking about using linear regression, which is what you use when you have one variable that's continuous and another set of variables that are also continuous. So this might be in the case of a single linear regression, be where you have one outcome variable or dependent variable and also one independent variable or predictor variable. You can also do something more complex where you have multiple independent variables all at the same time, in which case you call that multiple regression. So you'll remember from earlier in the semester that there's also another circumstance where we have two continuous variables. And that is where we are looking at a correlation. And so you might ask, if you just have these two continuous variables, why not just use correlation? Why use another analysis? So one difference is that here you are modeling the variables. That is, you're assigning what you think their role is. Where one is modeled as the independent variable, that is the variable that's influencing an outcome, and one is modeled as the dependent variable, that is the one that is being influenced. So when you're running this regression, you're basically coming at this research question thinking that one of them is causing or influencing the other. Whereas if you're doing a correlation, that means that you just think that they're related to each other, but you're not necessarily making an assumption about one causing the other. Whereas in linear regression, you are doing so because that's how you're setting up that statistical model. So if you do have one independent variable and one dependent variable, correlations and regressions will give you basically the same information. The p-value is going to be the same in terms of the statistical significance. You will get a different value for a linear regression for the test statistic. Rather than getting an R, you'll get a B, but you can actually convert that into an R just by standardizing it. So if it's just one variable for an independent variable, one variable for a dependent variable, there's not really that much of a practical difference in terms of what that information is going to tell you. However, one of the big advantages comes into regression when you have more than one independent variable. So you might want to see cases where you think that multiple things influence an outcome variable all at the same time, and you want to account for those all at the same time in the same analysis. So examples of where you might use linear regression, you might have questions about how a personality trait is related to important life outcomes. So maybe you have a hypothesis that those people that are higher in extroversion tend to have higher life satisfaction. So you can run a linear regression to test that hypothesis. You might also have hypotheses about how something that occurs at one point in time influences what happens at a later point in time. So maybe you think that household income at age 8 is going to have an influence on reading comprehension at age 16. So for example, you might hypothesize that people who are in higher income households when they're a younger child will have higher reading comprehension scores later on in their childhood, just as an example. You also might have a hypothesis about how brain functions might be related to outcomes such as reaction times. So maybe you measure how much activity there is in the prefrontal cortex at a specific point in time, and then you see if the activity in the prefrontal cortex is associated with reaction times with the same participant at the same time. You could also see if something like empathy predicts donating to a charity more. So you might have a continuous variable where people are higher or lower in empathy and higher and lower in how much that they donate to charity. with all of these, you could just run a correlation, but with a linear regression, what you could then do is you could see how strongly it's related in terms of when there's this much of an increase in the independent variable, there's this much of an increase in the dependent variable. And you can also put in more predictors. So maybe if you're looking at life satisfaction, just as an example, you can look at that in terms of extroversion, but maybe you want to account for other personality traits. So maybe you also include openness to experience as a predictor or neuroticism as a predictor and see what the unique contribution of all of those variables are. So you can add a little bit more complexity to that regression rather than with correlations where you can only really look at those two variables and how strongly they're correlated. So that's the main reason that we do a separate analysis for regression rather than just for correlations. And I've told myself I'm not going to make these videos too long because I actually do a lot of regression and I actually have a lot of opinions about how to do regression the correct way. So I'm going to keep to what's being talked about in the textbook, and then after I go through the textbook information, I'll give you a little bit more information about what you can do even more with regression beyond just doing very basic linear regressions, right? So how does a linear regression work? You do start with a scatter plot, similar to what you have with the correlation. You'll recall that you put one variable on the x-axis and one variable on the y-axis, and then you plot all of those points. And each of those points represents a set of data, such as the data from an individual participant, where, for example, there was one person way down here, around 8.5 in terms of hours of sleep, and had grumpiness level probably somewhere around 41, 42, somewhere in the area. So all of these represent an individual participant's data in terms of sleep and in terms of grumpiness. And you can glance at this and say, okay, that looks like a negative relationship. So that the more you sleep, the less grumpy that you are overall. So when you're doing a regression, you want to have the independent variable x plotted on the x-axis. And you want the dependent variable y plotted on the y-axis. And so if we're modeling sleep as the x and grumpiness as the y, here we are making the assumption that how much sleep you get influences how grumpy you are. And it seems here, if we're interpreting it that way, that the more you sleep, the less grumpy you are. So it decreases grumpiness, essentially. So that might be our takeaway from it. Right, so that start is pretty similar to a correlation. We could take the data from the scatter plot then and get an R and get a p-value for that R. If we're doing linear regression, our next step is that we are going to try to find a line that best accounts for that data. So you may recall from algebra that you had to learn y equals mx plus b. If you're doing anything with regression or a lot of statistics, you end up using that formula a lot. Y is how much the value of the y-axis is for a specific point. So here it would be ranging from 40 to 90. And there's two separate values that you'd be putting in here. One of those would be the intercept, which is the b value here. And that is how much we would expect y to be if x equals 0. The other value here is the slope. So this is the value that we put in for x, and this is basically for every unit of x, this changes that many units of y. So you would, if you run a regression, basically you get a line that goes over that scatter plot. And so the b value would be the value of y when x is equal to 0. So there's not actually a meaningful 0 point on this. So sometimes you get an intercept and it's not even in the range of your possible values. And that's because it's out of the range of the x of the possible values. But this allows you to plot that line. And then the main thing that we're usually interested in is the slope. And so that would be the value m here. So the steeper this slope is, the stronger that regression is. So what you find here is that you'll get either maybe a very flat slope or a very steep slope. You also see here that this could vary a lot more. So these are pretty tightly fitting to this line. There's not a lot of variability along those lines. This line seems to be a pretty strong fit for the data. If these dots were kind of all over the place randomly, this line probably wouldn't be as good of a fit for the data. In the textbook, it doesn't go over mathematically how you get this linear regression line. So I'm not going to expect you to remember that, but I will talk a little bit about that. This line is determined by what's referred to as ordinary least squares. So linear regression, the standard linear regression, is sometimes also called ordinary least squares regression. And essentially what this is doing is it's finding the smallest squared distance from the line. And so if you, for example, look at that regression line on the left, this is the best possible fitting line. And so it's basically minimizing how far each of those data points is from that line. The one on the right is not as good of a fit for the data because you see that there's a lot of points that are really far away. And so if you took the sum of squares for how far each of those data points is from that line, you would see that it's generally pretty far off. So this slope is basically going through getting as close to all of the data as you possibly can. And so essentially how this works is that there's an algebraic function where first you start with the very middle of the data point. So you take the mean of x and the mean of y, and that's the middle of your line. And so your regression line is always going to go directly through the mean of x and the mean of y. And then once you know the mean of x and the mean of y, then it's a basic function of algebra to put in, okay, how much are each of these data points above the mean for x, and how much are each of those points above or below the mean for y. And then if you add those up and average that out, it will give you that regression line. So again, I'm not going to be testing you on that, but that's the basics of how it works. The reason that we specify ordinary least squares as opposed to other types of regression is that there's actually a whole world of different types of regression analyses out there. Ordinary least squares linear regression just happens to be the most common one used in psychology. And I think the main reason for that is that a lot of our hypotheses in psychology are hypotheses that fit with this kind of thinking about variables, that people higher in this are also higher in this, or people that are higher in this are lower in this, or if you increase this, this will decrease. So making this pretty basic hypothesis about there being a linear relationship often applies. Outside of psychology, this isn't the most common, and again, there's a whole bunch of different types of regression out there. But this is, a start to looking at modeling how variables are related to each other. So that will be your first introduction to this idea of statistical modeling, where basically we're trying to make sense of the data with a model of how we think those variables are related to each other. And in this case, we're trying to find basically a line with an intercept and a slope that's trying to make sense of that data. So you could also have multiple predictors, in which case, and it would be a mess to try to draw it out. So multiple regression, there's not really nice graphs to explain that. But it's basically based on the value of a whole bunch of different x's, what would we expect the value of y to be? So for that, you'd be putting in the value of all of the x's that you have. So if you have 3 predictor variables, you'd have 3 values of x for each participant and 1 value of y. And then you'd be able to draw a line based on each of these 3 values of x. What would we expect the value of y to be? And then, of course, since you have multiple variables on there, it's not going to show up very nicely in a 2D graph. But that's essentially what is going on with linear regression, where with one independent variable and one dependent variable, it's finding the slope of that one independent variable predicting the dependent variable. With multiple predictors, multiple regression, it's doing the same thing, predicting the dependent variable, but based on the value of all of the independent variables simultaneously. Okay, so when you're doing this, this also enables you to do null hypothesis significance testing. So is the strength of this regression line stronger than just if you had random chance, random data points being generated? So you actually have 2 different hypothesis tests that you get for linear regression. So one of those is for the whole model. That is for the entire regression with all of the independent variables included. So if you have a null hypothesis, that would be that there is no relationship between the variables at all. If you have an alternative hypothesis, this is basically that you're arguing that the relationship is exactly what the regression line predicts. So I'm actually going to jump back a slide here. Essentially, the alternative hypothesis for the model for linear regression is that the relationship here between sleep and grumpiness is exactly this line. So with that, you actually are going to get the data to do an F-test because you have all of that variability, and you're seeing how much of the variability does that regression line account for as compared to all of the variability in the dependent variable. And so because you have variability accounted for as compared to all of the variability in the outcome, that will give you an F-test value. So you also get it for the coefficient. So if you have one predictor, there will just be one coefficient, which is referred to as the B. And so in the regression output, you'll get values for B. So for this, the null hypothesis is that B equals 0. So if we jump back here, it would essentially be that the slope is completely flat. And if there was no relation between the independent and dependent variables, you would just get a completely flat line, right? So then the alternative hypothesis is that the slope is not equal to 0. So again here, it could be either positive slope, that means going a positive direction, or a negative slope, like what you see with these where it's going in a negative direction. But it's a 2-tailed test by default, that it is not equal to 0. So null hypothesis of 0, alternative hypothesis that's not equal to 0. This might also seem familiar. For this, you will get a t-test. So you'll get a t value for that slope, and you'll get a p-value associated with that t-test. And it works essentially the same way, where it's looking at what the slope is for the line, and if you randomly generated values, how often would you get a slope that strong or stronger by random chance? So that is something that is sometimes a little confusing for people that are first starting at regression, because you're running one test and then you're getting 2 significance values, and therefore an F-test and a t-test, which are used to being used when you have a categorical variable, which intuitively does not make very much sense. And so that's something I found confusing for a little while myself when I was new to it. But essentially, it's because of the type of data and how it would vary by random chance, where for the model, if it accounts for a lot versus it not accounting for very much, that's an F test. If it's comparing whether something is the same as 0 or not the same as 0, that is a t-test. So that's basically why that works and why you get two separate values. So if you have, again, one independent variable and one dependent variable, this is going to give you redundant information. So your p-value for the model and your p-value for the coefficient will be exactly the same. So obviously, the amount accounted for by the whole model, you'll get an F, you'll get a T here. So those won't be exactly the same, but the p-value will be the same. So what is different is when you have more than one predictor. So if you have, say, two predictors, you're going to get a B for both of those predictors, and you'll have a null hypothesis significance test for both of those predictors separately. And then you'll get one for, again, the whole model, which will basically be testing whether all of the independent variables combined account for more variance than you would expect by random chance if nothing at all was happening. So in that case, the p-value for the whole model will most of the time be completely different than for each of those two coefficients. So that's when you have to start interpreting those differently. And I'll get into that when I start running the analyses in R. Right? So with a linear regression, there is actually a quite long list of assumptions. And if you wanted to get into more details, you could go over tons and tons of different assumptions. So when you get into trying to modeling a relationship between two variables or even more variables than that, you could start doing a lot of different stuff. The more complicated the stats get, the more assumptions that start going into things, essentially. So just like with t-tests and f-tests, there's assumptions of normality for both the independent variables and the dependent variable. There's also an assumption of homogeneity of variance, and that is for all of the independent variables. So a lot of that, how you test for it, what determines whether there's homogeneity of variance or not, whether there's normality or not, is going to be pretty familiar to what we've been doing the last couple of weeks. There's also an assumption that the relationship between the independent variable and dependent variable is linear. That is that for each increase in the independent variable, there's either an increase or a decrease in the dependent variable. And that's something that goes up or down at the same amount along that continuum. So how this could be violated is if the relationship is actually curvilinear. So it might be the case that maybe scores are high at the bottom end of the independent variable, and then they go down, and then they're high at the top end of the variable. So that is a U-shaped distribution. In that case, there might be a relationship between the variables, and there might be some causal factor going on that's causing scores to be high for your dependent variable when scores for your independent variable are both low and high. But you wouldn't be able to detect that if you were doing a linear regression, because the line wouldn't fit very well for that data. And you can, of course, get into a lot more complexity with that as well. But with this, again, we're just looking very basically at whether there is a linear relationship or not. If there's other shapes of relationships, we're probably not going to find them. You also are making assumption that the predictors, if you have more than one predictor, more than one independent variable, are uncorrelated. So it doesn't literally need to be a correlation of 0, but if the correlation between two or more independent variables gets to be really strong, basically the output of the regression isn't going to make any sense. There's going to be bias in both the parameter estimate, that is the estimate of the slope. There's going to be bias in the f-test for the model, and there's going to be bias in the p-values. So this is something that is not really a problem as long as your predictors aren't correlated super strongly, but when they're really strongly correlated, you can't interpret a linear regression at all at that point, right? There's some assumptions about the residuals for the regression. So that is after you account for that linear relationship between the independent variable or variables and the dependent variable, there's variance that's not accounted for, and that is left over. So maybe I'll jump back to those figures there, because that makes a little bit more sense. So like with this line here, each of these points is above or below that line. How much that varies is the residual. And then you have a whole bunch of residuals for each of those data points. So when you hear residuals, that's basically what it is, right? So you're assuming that the residuals are independent of each other. So it's not that the line is a good fit at the bottom of the distribution and then at the top of the distribution, the scores are just all over the place, for example. You can get into a lot of assumptions about residuals as well. We'll go over some of the basic ones that you need to look at for linear regression. And you also are making assumption that there are no bad outliers. That is, there aren't any outliers that are overly extreme or that throw off your estimates so much that the regression doesn't make any sense. So similar to that assumption about there being uncorrelated predictors, if you have maybe one outlier and it's not out too far, it's not really going to affect your results. It can be the case that if an outlier is completely different from all the other scores, almost all of the variance is going to be just that one outlier. So as I've talked about in class, if you compared the wealth of everyone in class to the wealth of Jeff Bezos, and that was in a regression, his difference from the mean is going to be a big chunk of the variability. The regression line is basically going to be, is Jeff Bezos higher or lower than the rest of the class? So not at all informative. But if you have outliers that aren't too far away, it's not a huge problem. So there's a lot of assumptions of linear regression. With most of the data that you're ever going to run, at least one of these assumptions is going to be violated at least a little bit. So that's not necessarily a terrible thing. It's just something that you want to understand with your data. So when we are looking at these assumptions, one thing I would caution with linear regression is that when you're doing these analyses, you know, in a textbook, you kind of learn this is the ideal situation. If you run psychology studies, there's going to be violations of assumptions for linear regression for almost everything that you do, unless you're making up fake data or you have just by chance like some amazing data that's super clean looking. So if these assumptions are not met, usually what we're doing is that we are checking the model to see what violation of the assumptions there are, and if there are, how bad they are. And then maybe we want to run a different type of analysis, or maybe we want to run the analyses a couple of different ways and inform the reader any potential violation of assumptions. So with linear regression, this is one of the most basic types of statistical modeling that you do. But with any statistical modeling, you're always going to be at least a little bit wrong. You basically are trying to figure out when you're doing this model how wrong you are and how much of a problem that is. Because we want our models to be at least a little bit informative. That is, we can account for what's going on in the dependent variable more than just, you know, flipping a bunch of coins and guessing what's going on. And so it's always somewhere on that continuum where maybe we are able to account for almost everything that's going on in the dependent variable at the one end, and our model meets these assumptions really nicely. And at the other end, we account for basically nothing, and the assumptions are violated anyways, so it's hard to interpret. There's a lot of steps involved in doing a regression, more than in a lot of other analyses. And this is basically, again, because we are developing this model that we think these variables are related to each other. They have this linear relationship such that for every unit you go up or down for one variable, you go up or down for this other variable. So with that, let's jump into how you run a linear regression in R. So I'll see you there.